Hello friends, session 3, PostgreSQL Architecture. This is the third lecture in the series of PostgreSQL DBA course or DBA training. If you're watching it on YouTube, please subscribe to the channel and press the bell icon so that you get notification whenever there's a new lecture on the topic. Because there's going to be a complete program on PostgreSQL. You'll not get all the lectures on YouTube, however, that is true. So for that, you need to visit the website, www.skillpedia.com, for complete lab assignments, lectures, and handouts. Agenda of the session is understanding the architecture, PostgreSQL architecture, memory structure, that is shared memory, shared buffer, write-ahead log buffer, then process structure, that is process types, Postmaster process, Backend process, client processes, and storage structure. So all in all, by the end of this lecture, you should be able to understand how PostgreSQL is organized in the memory as a process and on the disk. So understanding the architecture. Postgres was first released in 1989, and since then there have been a lot of enhancements to Postgres. According to DB engines, this is the URL, you can check it, and Postgres is fourth position as of July 2022. It is the fourth most used database. In this session, we will discuss PostgreSQL internals, architecture, and how various components of PostgreSQL interact with one another. Let's talk about the memory. Shared memory refers to the memory reserved for database caching and transaction log caching. The most important element in shared memory are shared buffer and write-ahead log buffers. What are shared buffers? The purpose of shared buffer is to minimize the disk I/O, that is disk input-output activities. Some of the principles which must be met. One is you need to access very large, that is tens of hundreds of gigabytes buffers quickly. You should minimize contention when many users access it at the same time. And frequently used block must be in the buffer for as long as possible. It is PostgreSQL database memory area. Shared by all databases in the cluster. Modified buffers are also called as dirty buffers or dirty area. Parameters. The parameter which can be used to performance tuning for this is shared underscore buffers. This sets the amount of RAM allocated to shared buffers. Is used least recently used algorithm to flush less frequently used buffers. Dirty buffers return to disk after a checkpoint. Memory components of write-ahead log buffers. The write-ahead log buffer is a buffer that temporarily stores changes to the database. It stores write-ahead log records. Means the data before go to the disk, it is from the memory, it is stored to a file. These files are called write-ahead log files. And once the data is returned to the files, then the data from memory go to the disk. The content stored in write-ahead log buffer are written to a write-ahead log file at the predetermined point in time. These buffers, write-ahead log buffers, return to write-ahead log segments on the disk. From a backup and recovery point of view, this write-ahead log buffers and WAL files are very important because they help in recovering the database to a consistent state in case of failure. Then memory components, we have work memory. This work memory parameter is the memory used by each query for internal sort operations such as order by and distinct. Postgres write to disk, that is temporary files, if memory is not sufficient, just like swap area. Maintenance work memory, this is the amount of RAM used by vacuum, create index, and reindex like maintenance operations and setting this to bigger value can help in faster database restore. Now the process architecture, the initial process is created by the fork system command, that is kernel system command, system call is the fork, and the postmaster process is the first process which is created. So postmaster daemon process, background processes, per connection backend process, and client processes. The postmaster process, the process I'm talking about here, this process is the first process started when you start PostgreSQL. At startup, it performs recovery, initialize shared memory, and run background processes. It also creates a backend process when there is a connection request, means whenever there is a connection request from the client, it creates a background process by making a fork system call. So backend process is created so that the client process and backend process can start talking to each other, which is so step number 1, connection request received, step number 2, fork system call made, and step number 3, send query request to and results which happen between client process and backend process. So the processes, the first is postmaster, and under that there are a lot of other processes like checkpointer, BG writer, archiver, write ahead log writer, logger, auto vacuum. Then per connection processes are created, like every user has user process 1, user process 2, and so on and so forth. How many users are connected, you'll have those many processes. So these are common for all, and these are per user processes. From the memory perspective, we have process memory, that is maintenance work memory, and work memory as I discussed. Then write ahead log buffers and shared buffers. Three main components. From the database, we have write ahead log files, the data files, archive WAL files, and global files. This is from the disk perspective, the storage part. The process architecture, the other processes as mentioned in the previous figure, are one with the logger. The job of this process, the role of this process is write the error messages to the log file. Then we have checkpointer. Whenever a checkpoint occurs, the dirty buffer is returned to the file. Then background writer. This is a background writer which write or flushes dirty data blocks to the disk. Then WAL writer, it writes the write ahead log buffers to the write ahead log file. Then auto vacuum launcher, it fork auto vacuum worker when auto vacuum is enabled. It is the responsibility of the auto vacuum daemon to carry vacuum operations on bloated tables on demand. Archiver, when in archive log mode, copy the WAL file to the specified directory. Then stats collector, DBMS uses statistics such as session execution information like pgstat activity, and table uses statistical information like pgstat all tables are collected. So what all background processes are there? We can check using ps-aef grab Postgres. I'm working as a Postgres user, the default user created after the installation. When I logged in and I use this, you will see the processes. There are 1, 2, 3, 4, 5, 6, 7, 8 processes. So this process is the postmaster, the main process, and this process launch other 7 processes: logger, checkpointer, background writer, WAL writer, auto vacuum launcher, stats collector, and logical replication launcher, as I mentioned in the table in the previous slide. If you check the relationship between processes with the ps-tree command, you will see the 4091 process ID. And if you use this ps-tree with -p ps ID 4091, you will see all processes are child processes. So this 93, that is 93, 95, 96, these are all child processes which comes under postmaster. This is the parent-child relationship. The maximum number of background processes is set by max connections parameter, and the default value is 100. The backend process performs the query request of the user process and then transmits the results. Some memory structures are required for query execution, which is called local memory. The main parameters associated with the local memory are work memory, as I mentioned earlier. This is the space used for sorting, bitmap operations, hash join, and merge joins. The default setting is 4 MB. Then maintenance work memory. This is the space used for vacuum and create index. The default is 64 MB. Then we have temp buffers. This is the space used for temporary tables and default is 8 MB. Client process. Client process refers to the background process that is assigned for every backend user connection. Usually, the Postmaster process will fork a child process that is dedicated to serve a user connection, specific user connection. The other processes are WAL sender, that is send write-ahead logs to replicas. One WAL sender for each slave connection for replication will be active. Accordingly, corresponding is receiver is started on slave, also known as standby or replica in replication. It streams the write-ahead logs from the master. Then BG worker. PostgreSQL is extensible to run user-supplied code in separate processes that are monitored by Postgres. Such processes can access PostgreSQL shared memory area, connect as client using libpq. Then we have BG worker, logical replication launcher, logical replication between the publisher and the subscriber. PostgreSQL does not use a direct input-output. When it needs a page, that is data block, it searches its own memory, that is shared buffers. If it is not found in the shared buffer, it will request the operating system for the same block. The operating system will then fetch the block from the disk and give it to the Postgres. If the block is not found in the operating system cache, then it is not found in the cache. So more important to caching when database and active data set cannot fit into the memory. The database structure, we have different concepts related to database structure. First is the items related to the database. Whenever you create a database, what does it mean to be a database in Postgres? PostgreSQL consists of several databases. This is called database cluster. When initDB is executed, template 1, template 0, template 1, and Postgres databases are created. The template 0 and template 1 databases are template databases, just like a model database in SQL Server and Sybase. For user database creation and contain the system catalog tables. The list of tables in template 0 and template 1 databases is the same immediately after initDB. However, template 1 database can create objects that the user needs. The user database is created by cloning the template 1 database. Items related to table space. The PG default and PG global table spaces are created immediately after initDB. If you do not specify a table space at the time of table creation, it is stored in PG default. If you recollect, we have something similar in MySQL, and InnoDB storage engine have a concept of table space, and there we have InnoDB IB data 1 table space, which is default created. In fact, table space is concept is there in Oracle also, and the definition, by definition, table space is what? It is the logical connectivity between physical representation and logical representation. It is a bridge actually, because on the disk it is a partition or file. On the database, it is the object. Table managed at the database cluster level are stored into PG global table space. The physical location of PG default table space is under this PG database. That's what I was referring to. So this is a logical entity as a database object, physical entity in the storage system. The physical location of PG global table space is PG data/global. One table space can be used by multiple databases. At this time, a database specific subdirectory is created in the table space directory. Creating a user table space creates a symbolic link to the user table space in the PG data table space directory. Then from the perspective of the table, there are 3 files per table in PostgreSQL. Similar to this MySQL database, because MySQL also have a .frm file, then .data file, multiple type of files. So here three files are there in Postgres. So one file is for storing the table data. The file name is OID in the table, or OID of the table, that is object ID. One is the file. There's one file to manage table free space. The file name is OID underscore FSM. And then third file is managing the visibility of the table block. The file name is OID underscore VM. And the index does not have underscore VM file. That is OID and OID underscore FSM are composed of two files. On the disk, we have a data directory. Just like in MySQL, we have data directories created when you initialize your MySQL instance. So similarly, here we have a data directory which is initialized using initdb in PostgreSQL, similar to MySQL d-initialize. It contains write-ahead logs, log files, databases, objects, and other configuration files. You can move write-ahead logs and logs to different directories using symbolic links and parameters. Environment variable for this is pgdata. Configuration files inside the data directory are postgresql.conf, similar to my.cnf for MySQL. Constraint contains several configuration parameters. Then we have pg_indent.conf, pghba.conf, and postgresql.auto.conf file. If you want to verify, you can use ls-l with, as I said, the path is stored in pgdata. So when you use ls-l pgdata, you will see the table space file base, the log files, global, then log files. If your system is not starting, if your PostgreSQL server is not starting and you are getting error in starting up the system, you can refer to the log directory, and there you'll find a very interesting file which will give you the exact reason why your PostgreSQL server is not starting. Then commits. Then we have this is the file I was referring to, pghba, pgindent, and then the auto.cnf file, postgresql.conf file, and this is a write-ahead log, pg_write-ahead log. So you see a lot of files in the data directory. The configuration files inside the data directory, which were mentioned here, one is pg_version. This file had a version string for the database cluster. Then there was one file, pg_hba.conf. This file has host-based access control, that is built-in firewall for PostgreSQL server. Then we have pgindent. This is indent-based access file for operating system user to DB user mapping, database user mapping. Then postgresql.conf. This is primary configuration file for the database. Then we have postmaster.options. This contains options to use to start PostgreSQL instance. Then we have postmaster PID, as the name suggests, it is a process ID or the postmaster process ID. PostgreSQL.conf file versus PostgreSQL.auto.conf. PostgreSQL.conf file, configuration file for PostgreSQL, similar to my.cnf for MySQL. This file contains the parameter and values required to run your PostgreSQL instance. The parameters are set to their default value if no modification is done to this file manually. Located in the data directory or /etc depending on the distribution you choose, and the location can be modifiable. Then the PostgreSQL.auto.conf file. This gives Oracle-like compatibility to modify parameter using alter system. Any parameter modified using alter system is written to this file for the persistence or the system reboot. This is the last configuration file read by PostgreSQL when started, empty by default, always located in the data directory. View or modify the parameters in PostgreSQL. To use show to view a value set to a parameter. Like you can use psql-c show work memory. That will show your work memory parameter. To see all the settings, you can use show all, like psql-c show all. Modify a parameter using value by manually editing the postgresql.conf file. You can directly edit the file. Use alter system to modify a parameter like psql-c alter system set archive mode to on. Then we have pgctl-d. You need to restart your system because you are altering the system parameter. So you need to start the PostgreSQL server. Use reload using following syntax to get the changes into effect for a parameter not needing a restart, that is select pg reload configuration or pg control -d reload, that is pg data reload. The base directory contains, as I mentioned, contains the subdirectories for every database you create. Every database subdirectory contains files for every relation or object created in the database. The data files. Data files are the files for a relation in the base directory. Base directory contains relations stored on the disk as 1 GB segments. Each 1 GB data file is made up of several 8 KB pages that are allocated as needed. Segments are automatically added, unlike Oracle. So you have a couple of commands which can be used. For example, to create a database like skillpedia, you can use the command psql-c create database skillpedia. And this is the command. You'll get a simple message, create database. That's it. Get the data ID of the database and see if it exists in the base directory. The command is select DATID, that is data ID, DAT name from PG start database where data name is skillpedia, and you can expect this output which is displayed here. Create a schema. You can similarly create a schema pg psql-d-c create schema pgdba. Create a table named employee in the pgdba schema. psql-d skillpedia-c create table pgdba.employee, and the details are, these are the parameters we are creating. So these are the screenshots of the command. psql-d skillpedia create schema, then -d skillpedia create tables. So you qualify your table name with the schema name, just like Oracle you do. Locate the file created for the table that you can use in the pgdba.employee in the base directory with this command psql-d skillpedia-c select pg relation file path pgdba.employee. Base directory block size. Check the size of the table in operating system and value of the parameter block size. psql-c show block size, and that you can see here it is 8 KB. So that's the output. Insert a record in the table and see the size difference. So you insert a value 1 and Seattle. Once you insert this value, you'll see the difference. Insert more record and check the size difference. So this is how you enter multiple records. Generate series 2 to 100,000, 10,000, 2 to 1,000, that is 0 to 199 records you will see here, because you are entering here first value is there, so value insert at 0, one number of records is entered. Write ahead logs. Write ahead logs. When client commits a transaction, it is written to write ahead log segments on the disk before a success message is sent to the client. Transaction journal, also known as redo logs, similar to InnoDB buffers in MySQL. Written by write ahead log writer background process. Write ahead log ensures durability with AppSync and synchronous commits set to on and commit delay set to 0. It is used during the crash recovery. Size of write ahead log is 16 MB. It is modifiable during initialization. Created in pgxlog directory until Postgres 9.6. Location of the WAL is renamed to pgwal from Postgres 10. The write ahead log directory exists in data directory by default. It can be modified. WALs are deleted depending on the parameter, WAL keep segment, and checkpoint timeout. WAL archiving. Archived var write ahead log files, the way we have logs which can be archived in Oracle also. So WALs in pg underscore wal or pgxlog are gone after certain thresholds. Archiving ensures recoverability and helps a slave catch up during replication lap. Archiving in Postgres can be enabled through two parameters. One is archive mode or archive command. It ships WALs to safe location like backup server or the cloud storage like S3 or object store. WALs are archived by archiver background process. Archive underscore command can be set with the appropriate shell command to archive write ahead logs. Let's enable archive. Command is alter system set archive mode to on. Alter system set archive underscore command to CP. This is your system command you are copying where you want to copy your logs. pgctl restart your PostgreSQL server. What if archiving is failed? If archive has been enabled and the archive command failed, then the WAL segment for which archiving failed will not be removed from the page WAL or page X log. An empty write ahead log file name .ready is generated in the archive status directory. The background process archiver attempts to archive the failed write ahead log segment until it succeeds. And there is a chance that pg underscore wall directory can get filled and does not allow any more connections to the database. That's all for this session. If you enjoyed the session, go for the complete course on the website www.skillpedia.com. And if you really like the session, please hit on the like button and press the bell icon. Thank you so much. Bye-bye.